All right, so in this next segment, we're going to look a little more carefully at phase diagrams. So specifically, we're going to interpret key parts of the phase diagrams and make sure we understand what's where and why. And then we're going to understand a heating curve for a substance undergoing phase transitions, going back and forth between a phase diagram and what that means in terms of, say, what temperature you would be at and what phase you'd be in, given the amount of heat you've added. Okay, so again, this is what a phase diagram might look like. So an important part on phase diagrams is the critical point. The line goes up dividing liquid and gas here until we get to a certain point. You notice there's no dividing line above that. And something really interesting happens. Like above that point, once you reach, this region up here, you stop having a distinction between the liquid and gas phase. So if I were to go from here to here, what I'd see, I'd transition from a high density phase to a low density phase once I hit that point. But if I'm over here, I'd go continuously from high density to low density without actually having any change of phase. You can have very interesting behavior where you start over here, you raise the pressure, go over, increase the temperature, and then lower the pressure and cool it down. And you can get from a liquid to a gas phase without ever going through a phase transition. Yeah, so for a given T, then at low P, you get a phase transition, but at high P, you don't at a given temperature. So that's a critical point. And it's a little hard to really think through this. So there's a nice link that I've shown, supercritical CO2. The link will be on the webpage, and you really should look at that just to get a sense of what's going on. There's some nice experiments where people take this little bubble of carbon dioxide and heat it up and down and change the pressure in various ways, and you can see really interesting phenomena. There's some an interesting phenomena called critical opalescence, that once you're at the critical point, it actually essentially can't decide if it's a gas or a liquid on sort of a macroscopic scale. So you get these bubbles of gas and liquid that essentially of macroscopic size. And so it looks transparent, and all of a sudden it gets cloudy because literally at that point it can't decide if it's a gas or a solid. So sorry, a gas or a liquid in this case. So the critical point is pretty important if you want to be avoiding the phase boundary for whatever region. Okay, so we got the critical point above which you don't get separate phases. You just have a supercritical fluid. So fluid can apply to either liquids or gases. So if you're above that temperature or above that pressure, then you only have a critical fluid. Okay, so let's be specific. Let's look at the CO2 phase diagram, and let's look at it, just make sure we understand it, answer some questions. What's the minimum pressure at which liquid CO2 can exist? So we look here, we give down the pressure, and we notice, aha, below a certain pressure, in this case 5.11 atmospheres, liquid CO2 can actually exist. You can have solid, and you'd have a transition as you go up in temperature between solid and gas, which is exactly what you see when you buy dry ice in the store. You just have liquid CO2, so vapor CO2 coming out. There's no liquid coming out. It just goes directly to vapor. Then goes away. Be very careful. You don't want to be like, if you have an enclosed area and you have a bunch of dry ice, you don't want to be near the floor because there'll be too much carbon dioxide and you'll have a hard time breathing. It's not poisonous, but it just, it sinks below the oxygen, and so it crowds out air with oxygen because the partial pressures are going to be equal no matter what the composition is. So if you have a higher composition of CO2, you'll have a lower composition of oxygen. So that can be problematic. So if you have a higher concentration of CO2 at the same pressure, you must have a lower concentration of oxygen. That'll go up towards the ceiling, which is problematic. Okay. What's the critical pressure? Well, the critical pressure is going to be the pressure above which it can no longer be a liquid. So that would be, the critical pressure would be here. And what happens when the pressure is reduced from 72 atmospheres to 5 atmospheres at 28 degrees C? Well, 28 degrees C, if we go from 72 atmospheres to 5 atmospheres, then we'll be going through a transition from liquid to gas. If we do it at 33 degrees C, then we will have no transition from liquid to gas. It will simply be a fluid of varying densities. One other point that came up when we looked at the minimum pressure with which liquid CO2 can exist is the triple point. So the triple point is an interesting point, is it's in equilibrium with solid, liquid, and gas. And you can show that there, if there's three phases, there'll always be a triple point, that there's some interesting thermodynamic inequalities that show that you have to have a triple point if you have three phases. So yes, that has less applications than the critical point, since there's a lot of uses for supercritical fluids. But triple point has less immediate practical applications, but it's an important point to find on a phase diagram.